Welcome everybody to this episode of Functional Programming 101. And in this lecture, we're going to do something slightly different. We're not going to introduce new concepts. What we're going to do is we're going to show you how a typical transformational development of programs in Haskell works. So the general pattern is that you start with an obviously correct solution that usually uses a lot of brute force and is super inefficient. And then you use refactoring to make it more efficient. All right? But the first goal is to write the simplest program that works, no matter how inefficient it is, and then you start refactoring it. So there's many similarities with, extreme programming and things like that, Just do the minimal things to make it work, and then later we will kind of try to optimize it. And maybe it's not necessary to optimize it, because even if something is quadratic, maybe you never use it on big inputs, or all the inputs that you get can run in reasonable time, and you can spend your time better on other things. So no premature optimization. Make sure that things are correct first and then optimize later. One thing that we won't show here is that you can also take your Haskell code, use it as a prototype. Once you're happy with it, you implement the same algorithm in another language that is maybe more efficient. But, depending on the particular program, the Haskell compiler might already do a good job, but sometimes it's not just about speed that you want to use a different language, but it is because in your company they are not using Haskell, but say PHP. Okay? And remember, one of the mottos of this course is think like a fundamentalist, but code like a hacker. All right? So, and this is what we will see here. We start with a very fundamentalist thing. It has to be correct. And then we kind of, will hack on the code to make it more efficient. And the problem we're going to look at is the so-called countdown problem. And countdown problem is based on a quiz program on British TV that has been there for a while. It's originally based on a French TV show. And in that show, there's a game that we call here the countdown problem. If you Google for a Sudoku solver in Haskell, or if you read any of Richard Bird's papers, you will see a very similar development. So this is very idiomatic Haskell development. So let's look at what this countdown problem is first in an informal way. What we need to do is, given a set of numbers and the standard operators, addition, subtraction, multiplication, and division, we need to create an expression whose value is some given value. So in this case, we say we have to create an expression whose value is 765. Now, for humans, this can be hard, because the search space is rather big. So we have to kind of try all possible combinations with parentheses and whatever to find the answer. So this is fun in a quiz show. And some people are really good at it, can do it fast. Other people will kind of fail. But this is something computers are good at, right? Because computers have infinite patience, so they can turn through this search space and find the solution. And if we can restrict the search space enough, it might even be able to find these solutions very quickly. And that will be the case for this example. Okay? There's a couple of more rules. Is that all numbers, including intermediate results, must be natural numbers. They must be positive. Each of the numbers in the original set can be used only once. And And then there's another set of rules, but you know, we keep things simple right here. So in particular, let's look at a possible solution. In our case, using the numbers 25, 10, 50, and 1, we can create 765 as follows. And notice that, you know, 25 minus 10 is a positive number. 50 plus 1 is a positive number. And when you multiply two positive numbers, they are positive as well. All right. So for this particular example, the search space consists of 780 possible solutions. But if we slightly change the result value, then suddenly we can find no solution. Okay? So we go from 780 possible solutions to no solutions. Okay, let's start to build this solution to this program bottom up. Okay, so we're going to start by building the pieces, and then we glue everything together to solve the problem. Oh, what am I doing? Eric, come on. Don't make a mess. Okay, here we go. So what we're going to do is we'll define our operators as an algebraic data type. So we have addition, subtraction, multiplication, and division. And what we're going to do is we're going to define an evaluation function that takes two numbers and applies the operator. Okay? And it's straightforward. Whenever you want to add two numbers, you add two numbers. Whenever you want to subtract them, you subtract them, etc. And the reason we're using this representation and not immediately evaluating them is because we want to build a symbolic representation of the expression, because we don't want to find the number 765. We want to find an expression that when you evaluate it will return this number. So we want to do symbolic processing of expressions. And then once we have an expression, we can evaluate it with this function. Now let's encode the rules of the game. So one of the rules was that every operator must be applied to positive numbers. So let's check whether when we apply an operator that it's a valid application of that operator. So if we add two numbers, well, we don't have to check, because if we add two positive numbers, the result will be positive. If we subtract two numbers, we must make sure that the first number is bigger than the second number, because otherwise the result would be negative, and that is not allowed. Multiplying two positive numbers is always positive, and when we divide two numbers, we have to check that they are actually divisible, because otherwise we don't get a natural number. Okay? And now we can define the data type of expressions just as we have seen before. So we have a slightly different, instead of having like a separate constructor for each operator, we have one application that takes these operators. Good. So how can we evaluate an expression? Well, we evaluate an expression and we either return a singleton list that contains the value, or when the expression is not valid anywhere inside, we return the empty list. And you will recognize this trick from our parsers, right? Our parsers also returned either an empty list when they failed, or a singleton list with the result when they succeeded. We don't use the maybe type, we're using lists because it's much more convenient. All right? So if you are a Haskell programmer and you're using the maybe type, please reconsider to use lists. Because as you see here, it's a little bit nicer because you can use list comprehensions like this. Okay, so let's see how the evaluation works. Again, it's defined recursively over expressions. We either have a value, well, in that case it succeeds if the expression is, the value is greater than 0. And if we have an expression that is the application of an operator to two sub-expressions, what do? We evaluate the left-hand side, we evaluate the right-hand side, we check that the application of this operator to these numbers is valid, and if that's the case, we return that application there. Okay, so really what you see here is that it's an evaluation intermixed with a filter for only valid sub-expressions. So now let's continue to formalize the problem. There's a few more helper functions that we need. And these helper functions, I will just assume that they exist. But, you know, you will get them in your exercises. So I can assume that they exist, but you will have to define them. That's the, you know, the advantage of teaching a course. So the first function here that we're going to use is choices. So choices takes a list of values of type A and returns a list of lists that gives you all possible ways of choosing 0 or more elements from this input list. Okay? It's not as complicated as it sounds. Let's look at a concrete example. So if I want to have all the choices of the list 1, 2, so these are all the possible ways of choosing 0 or more elements from that list. So I can choose 0 elements. I can choose 1 element, so that can be 1 or 2. And then I can choose 1, 2, or I can choose 2, 1, because those are two possible ways to choose two values from that list. All right? So you see that thing here. And again, I will assume that this function exists. You will have to define that in the exercises. Now we can define a new function that, given an expression, returns a list of all the values. So all the values, so what are those? Those are all the values at the leaves. So if I have a value, I return a singleton list. If I have the application of whatever operator, I take the values of the left sub-expression and combine them with the values of a right sub-expression. So now we can decide if some expression is a solution for a given list of numbers by more or less directly translating the rules of the game into this Haskell program. So given an expression, this is our list of initial numbers. This is our target number. Now we have to check whether this expression here is a solution to the problem. Okay? So what this says is that, first of all, the expression must evaluate to the number that we're looking for. Okay, so that was the number that we're required to find. So when we evaluate the expression, it must use that number. And then, when we take all the values in that expression, and we take all the possible choices for the input numbers, that thing, that list, must be a member of that list. Right? So if you go back to the English description of the countdown problem, you will see that this is a very nice direct translation of that definition. So now let's look at a brute force solution that searches for all possible solutions. And to do that, we will use another function that you will have to define in the exercises. And this is the function split. And split takes a list and returns a pair of lists inside another list. And it will give you all the possible ways that you can split that list into a pair of lists. All right, so if I want to split 1, 2, 3, 4, I can split it into 1, 2, 3, 4. I can split it in 1, 2, 3, 4. I can split it in 1, 2, 3, and 4. And note that we don't take into account the empty list. So splitting 1, 2, 3, 4 into 1 and 1, 2, 3, 4 doesn't really make sense, because then I have not really split the list. I've just kind of, split off the empty list, which is kind of nonsensical. Okay? So again, this is a function that you will have to write in the exercises. All right, so now we can define a function that, given a list of integers, will return a list of expressions whose values that are in that expression are exactly that list of given numbers. So if we're given an empty list of numbers, well, then we can build no expression. If we are given a singleton list, well, the only expression we can build that contains that value is the expression that contains that value. Now, if we are given a list of numbers, how can we build all the expressions? Well, we split the list and then recursively use the left side to create an expression, the right side to create an expression, and then we're using our combine function to combine the two. All right? So this is a brute force way of enumerating all possible expressions that are built out of these numbers. Okay? And the combine function here just tries to combine these two expressions using any of the operators. And then what we can do is we can write a list comprehension that says, give me all the choices for this, the input list, brute force create all the expressions, and make sure that the value that I'm looking for is the required value. Okay? So, this solution here is a more or less one-to-one translation of the original problem. It's super brute force, but it works. Okay? So it works. If we run this on, like, a very, very slow laptop, and we look for the solutions to our original problem, it finds the first solution in under half a second, and in under a minute, it finds all solutions. Okay, so even for this very simple brute force solution, this is kind of fast, and well, it takes like about a minute to find all the solutions. The question is, can we do better? And we definitely can. Since we are brute forcing all possible expressions, there will be many expressions that are invalid and that we kind of have to filter out later. So if we can make sure that we are not generating any invalid expressions, that is definitely a win. And just let's do a back of the envelope calculation here. There's possible expressions that we can build are 33 million, and only 5 million of them are actually valid. Okay? And then what we will do is we will combine the generation function with the evaluation function. So we will fuse these two to make sure that things are rejected earlier. But before we do that, this sequence was rather long, so let's take a well-deserved break and then see you in a bit. Thank you.